Hello and welcome back to another video from the Waste Tutor. This is the second video and the last video of the Arithmetic and Geometric Sequences unit. In this video we're going to be going over geometric sequences and series, where in the last video we went over arithmetic sequences and series. So let's move into the unit overview. So in this video what we're going to be talking about is similarly to the arithmetic sequence and series. We're going to be having a look at the recursive definition of a geometric progression or a geometric sequence. We'll also be having a look at the general term, how do we define the general term of a geometric sequence, and also one of the things that switches things up, having a look at the limiting behavior as a geometric sequence progresses to infinity, as the number of terms tends towards infinity. And in special cases we can see that a geometric progression starts to tend towards a certain term. We'll also be having a look at the general geometric progression, geometric series formula to determine the sum of a geometric sequence. And we'll also be having a look at infinite geometric sums and the limiting behavior of infinite geometric sums. We'll also be having a look, just like we did in arithmetic sequences, we'll be having a look at how geometric sequences and series can be used to model compound interest, for example. And so where geometric sequences and series represent compound interest, arithmetic sequences and series represent simple interest. So let's get straight into the video. Okay, so in terms of what a geometric sequence is, first of all, where arithmetic sequences involve a common difference between successive terms of the sequence, geometric terms involve a common ratio. Okay, and so if we look at any term in a geometric sequence, we'll see if it progresses in this way, for example, that there will be a common ratio linking each of these terms in the geometric progression. Here we have our initial term a equals 1, and we have a common ratio of 3. We multiply by 3 each time. So, in terms of the recursive rule of a geometric sequence of this nature, we know that a nth term will be equal to the term immediately preceding it multiplied by our common ratio. And I'll call this common ratio r. We can similarly write this as tn plus 1 equals tn multiplied by r, as is done in the syllabus up here. But the main thing here is that the term here is 1 greater than the term here. Okay, and so this is the recursive rule of a geometric sequence. If we want to look at the general term of a geometric sequence, the general term, will be given by the initial term. The information that we need is the initial term a, and we also need the ratio r. And again, remember that whether we label the initial term as t0 or t1 does have a bearing on what we use here. So, the general term of a geometric sequence will be known as tn equals t1 times r to the n minus 1 if we label the first term as t1, or if we label the first term as t0, it'll be t0 multiplied by r to the n. And if we want to actually come to a real definition of what the geometric sequence is in the recursive rule, we also need to know what our initial term is. So the sequence above is given by the recursive rule of tn equals tn minus 1 multiplied by 3, where our initial term, t1, is equal to 1. And in our general term, we have tn is equal to t1, because we've defined t1 as our first term. And so because we've defined it as t1, our r common ratio will have to be to the power of n minus 1. So we've come to a definition of the general term of a geometric sequence. If we look at this as well, each term is multiplied by a common ratio r. This mirrors what happens in an exponential equation. If we look at 2 to the x, for each increase in x, as x increases, we have y being multiplied by 2. So for 2 to the 1 we have 2, 2 to the 2 we have 2 times 2 is 4, for 2 to the 3 we have 4 times 2 is 8, and so on and so forth. Therefore, the general term, or the recursive term for a geometric sequence or series is has an exponential nature, where the arithmetic sequence has a linear nature. Okay, now let's take a look at geometric series. In the case of geometric series, we have special cases where our geometric series converges to a specific term for an infinite geometric series. This isn't the case for an arithmetic sequence or series, since the sum of the terms will, by definition, tend to either positive infinity or negative infinity. As we can see, 1 plus 3 plus 5 plus so on and so forth. This sum will necessarily tend towards positive infinity, and 1 minus 2 minus 5, sorry, this should be 5, 1 minus 2 minus 5, and so on and so forth. This will tend to negative infinity by definition. Since positive infinity, this tends to negative infinity. In the case of geometric series, if our term r, our common ratio r, is greater than 1 or r is less than negative 1, then that will imply that our sequence diverges. And so if we have sum greater than 1 and we have 1 times 1.1, for example, we'll go 1.1, we'll go 1.21, and so on and so forth. And essentially, these terms will eventually tend towards positive infinity. And the same case with negative 1. What happens is we have 1 going to negative 1.1 and then back up to 1.21, and so on and so forth. And eventually we spiral up terms tending towards positive infinity and terms tending towards negative infinity. So if the common ratio in our geometric sequence or series is greater than 1 or less than negative 1, we will have a geometric series that does not have a limiting nature. It will tend towards positive infinity or negative infinity. However, if we have a geometric sequence or series with values between 1 and negative 1, negative 1 and 1, what happens here, as we successively add more terms to our arithmetic sequence or series, we have our initial term t1, we have r to the n minus 1, and if we consider this term r as being less than 1 or greater than negative 1, we know that as we raise it to steadily higher powers of n, this is going to tend towards 0. So r to the n minus 1 will tend towards 0 as n tends towards infinity. Okay? And so if we have, like, for example, 0.1, or we have 4 over 5 is our common ratio, and we raise it to n minus 1 where n is infinity, and infinity minus 1 is essentially just infinity, we know that that'll be 4 to the infinity over 5 to the infinity. 5 to the infinity will necessarily be much, much larger than 4 to the infinity, and as a result, this entire term just tends towards 0. And so for an infinite geometric progression where the common ratio is between negative 1 and 1, our geometric sequence will the nth term of our geometric sequence, where n tends to infinity, is going to be equal to 0. And in some cases, that even leads to our infinite geometric sequence tending towards our infinite geometric series, the sum of all geometric sequence terms, tending towards a specific value as we infinitely add geometric sequence terms. If we look at the general formula for a geometric series, though, not specifically related to questions of infinite sums, we can also derive a formula for a general geometric series formula. So if we have Sn, we know that it'll be defined as a plus ar plus ar squared plus so on and so forth until we reach arn. And if we want to determine an easily computable, something that we can compute easily, we have to simplify this. And the way that we do this is we multiply our infinite sum by r, giving us ar plus ar squared plus ar cubed plus so on and so forth until ar to the n plus ar to the n plus 1. Okay, and we can see that this is essentially a frame shift 1 unit to the right. So that A maps onto A times R, AR maps onto AR squared, and so on and so forth. And so if we subtract Sn minus R Sn, we can write that as A, and then all of these terms here will subtract. These will all cancel out, leaving us with A minus AR to the n plus 1. So if we factorize, we get 1 minus R multiplied by Sn equals A take AR to the n plus 1. And so the sum of an arithmetic series is equal to AR n plus 1, where A is our initial term. We can take the A out, giving us A, 1 take R to the n plus 1. Over 1 take R. It should be noted that in this case, because we've got our n plus 1 here, our initial term A is defined as T0. Okay? Because in this case we have A times R to the 0. Okay? Here we have A times R to the 1. Here we have A times R to the 2. And this is our third term, this is our second term, and this is our first term. And so in this case, we have T0 times 1 minus R to the n plus 1 over 1 take R. So that's equivalent to T0, 1 take R to the n plus 1 over 1 take R. We can also write that as T1, 1 to the R to the n over 1 minus R. This is equally valid. And so we can use this formula to generally compute the infinite series as well, or just general geometric series. In the case of compound interest, what generally happens in compound interest is that after each atom, we have a compounding or an addition of interest to whatever we initially have in the bank account. So if we had 1,000 at the end of one atom, we would compound and we would add a fixed interest rate. And at the end of the next atom, we would add interest in relation to what is currently in that bank account. So that is the initial rate plus the interest added from the previous atom. So if I take an example and I take 1,000 for example, and let's say I have a 6% interest rate. That would mean after 1 year I have 1.06 times 1,000, which is 1,060. At the end of the next atom, we would be having 1,060 times 1.06 squared, and whatever that's equal to, and so on and so forth. So, if we look at this, we can see that this sort of mirrors what an arithmetic sequence looks like. What a geometric sequence looks like, sorry. So, if we initially have our initial value 1,000, and we consider how much interest we gain, we know that it will be related, the amount of interest that we gain will be equal to a geometric sequence with initial term 1,000 and the common ratio 1.06. So if we consider after n terms or n atoms, we know that the amount of money in our bank account with compound interest will be equal to 1,000 times 1.06 to the n minus 1. Okay, and this will tell us how much money we have after n atoms. And so as a result, we can represent compound interest as a geometric progression. So, in this video, we went over the recursive definition of a geometric sequence given by Tn plus 1 equals Tn times R. We also went over the general rule, Tn equals T1 to the R to the n minus 1. You can equally write that as Tn equals T0 R to the n if you want to. And we also looked at the limiting nature of geometric sequences for common ratios between -1 and 1. We then had a look at the general form for a geometric series and saw that geometric sequences and series could be used to represent instances of compound interest. And there are a couple of other applications that will be provided in your Sadler textbook, and you can have a look at that. I have linked the chapter description in the comments below, in this video description below. So I just wanted to thank you guys for watching. Remember to comment if you have any questions or if I've missed anything in this topic. Subscribe so you don't miss any new videos. And the next video on where I introduce differential calculus will be released on the 14th of November. Thanks for watching, guys. See ya.